And good morning. Are we awake? You ready for a good day of listening and learning? All right. Well, welcome to the Dorothy Marie Lowry Distinguished Guest Lecture Series. We're so glad to have you. I just want to thank so many of you who have talked to me after the talk last week. It was a half-hour preparation time. And I got tons of email. I haven't responded to all of it yet, but I will. Those who have asked questions, I'm glad to respond to that. But thank you so much for that. That was really nice. And it was a good kickoff for our whole class. We're going to have a great semester. And I just hope you come back every single week. You know, I found talking to you all, sometimes you think, I don't know if I'm going to go hear that person because I don't really care about blah, blah, blah. And you come anyway, and you go, wow, I have never thought about that. And that's very interesting. And it stimulates you, and you get good conversations going among yourselves, and that's great. So I just recommend you come to every single session. It's good stuff. Today we have an amazing person. We're really looking forward to our lecture today. Let me just give you a little some of the little antipasto, a little bit about what we have to expect over the semester. Next week we have Dr. Jorrit Gaines talking about the neuroscience of healthy cognitive aging. She's an expert in her field. We have experts coming to talk to us about these things. Sam Ehrman from USC is going to come talk to us about the Supreme Court, how it gets formed and all that. Isn't that something that's pretty relevant and interesting in the times we live in? The week after that, we have representatives from Camp Pendleton. Some officers come to talk about how Camp Pendleton and the Marines have affected America and affect the world, local. They're right here. And you see Camp Pendleton there, and you drive by it, and you don't know much about it. And I thought it'd be great to have someone come and talk about the Marines and Camp Pendleton and how it has affected our world. So that's going to be a great talk. We have Martha Barnett, who's a well-known linguist. She does a show called The Way with Words that's very popular on NPR-type stations. And she's going to talk about language and linguistics and how it changes around the world. It's very interesting. You're thinking, I don't know anything about linguistics. Let me tell you, you want to come for that one. It's really, really interesting to think about how language affects us. Well, anyway, today I'm going to introduce Dr. Jeffery Krichmar. Jeffery L. Krichmar received a BS in computer science in 1983 from the University of Massachusetts at Amherst, an MS in computer science from the George Washington University in 1991, and a PhD in computational sciences and informatics from George Mason University in 1997. He spent 15 years as a software engineer on projects ranging from the Patriot missile system at the Raytheon Corporation to air traffic control for the Federal Systems Division of IBM. From 1999 to 2007, he was a senior fellow in theoretical neurobiology at the Neuroscience Institute. He currently is a professor in the Department of Cognitive Sciences and the Department of Computer Science at the University of California, Irvine. Dr. Krichmar has nearly 20 years of experience designing adaptive algorithms, creating neurobiologically plausible network simulations, and constructing brain-based robots whose behavior is guided by neurobiologically inspired models. His group has created and supports a simulation environment for developing large-scale spiking neuron networks. Say that 3 times fast. Dr. Krichmar has over 100 publications and holds 7 patents. His research interests include neurorobotics, embodied cognition, biologically plausible models of learning and memory, neuromorphic application and tools, and the effect of neural architecture on neural function. He's a senior member of IEEE and the Society for Neuroscience. Please welcome Dr. Jeffery
Good morning. Thank you, Greg, for that wonderful introduction. And I know it was kind of word soup. We might need that linguist to translate what, what I do. But I'll go over in detail what all those crazy words mean. And the bottom line is I'm trying to make a smarter robot. And I'll give you the reasons for that as we go forward. Now, I'm at UC Irvine, as Greg said. The UC Irvine mascot is the anteater. So when we established our lab, we said it was the Cognitive Anteater Robotics Laboratory. So I think every robot that we've made at UC Irvine is called Carl something or other. Okay, so our robots are called Carl. But I know Greg did a really nice job going over my troubled past, if you will. But let me just talk a little bit about my background. I grew up outside of Boston in Lexington, Massachusetts, which was an important town for the Revolutionary War. So we were called the Minutemen. And then I went to UMass Amherst, which was also the Minutemen. I got my degree in computer science. I worked for a while. We'll talk a little bit about that. Decided to go, had an interest in artificial intelligence. And so I went to George Washington University and became a colonial. I pretty much took all the classes that I could at George Washington, and I had to work to pay off some bills. So I was working and going in the evenings to George Mason University in Virginia, which is called, then I was a patriot. So you see there's a theme here. And I'm also a New England Patriots fan, so. Hey, oh, good. I thought I'd get boos when I said that. I don't know how this happened. It's not like I'm the most patriotic person in the world, but there you go. And my first job out of college was working on the Patriot missile system at Raytheon. So there's some sort of theme here. And the Patriot missile system was interesting. I would work literally in these Army trucks, programming software to handle the radar, the communication, and also the Patriot missile system is a defensive missile system. So a lot of times I go out to the desert in New Mexico to test software. So it was very interactive with what was going on with the machines. And this picture of Japan, this is Nagoya, Japan. I had the opportunity to help the Japanese Defense Administration set up their own missile defense system. So I spent about 6 months or so in Japan actually working on systems like this. And like I said, after this, I got interested in artificial intelligence, started taking courses in grad school. Like many students, I had lots of loans to pay off, so I would work during the day and go to classes in the evening, at least at the beginning. And that led me to a job at IBM doing air traffic control and making a new system. And again, that was very interactive, having to work with displays and also the buttons and all this to make it more intuitive for these air traffic controllers because they really have a high workload. And another job I had along the way was working at this company. So this company called PMI was developing a machine that would measure eye movements. And this got me more into the neuroscience thing. So if you measure eye movements, you can tell a lot about a person if they're on drugs, if they're drunk. But what we found out is also sleep deprivation. So your eyes actually get slower when you're sleep deprived. And so this was an interesting working like out how to track an eye and also test the eye movements and then actually record that and see if they actually were impaired. And I like this picture. A friend of mine sent this. He was going through his basement, and I forgot about this. When I was at this job, it was near Washington. The Washington Post did an article on our work at this startup, and that's me, a cartoon figure of me, actually. And I like it also because over time, Washington Post on Science Tuesday would have pictures of someone working on a microscope, and then I would show up again doing a microscope. So they were using me as like stock photo. Okay, so why do I go through this? I did want to say, like, most of my interest in computer science was having computers make things happen and having computers read information from the real world and then respond. And that's one of the reasons I got very interested in robotics. But as I was doing my studies, I took a couple courses in psychology and also neuroscience, and I really got very interested in how the brain works. And so I took my first neuroscience class, and it was a pre-med class, and I was really struggling because these pre-med students, you have to name all these different nuclei and tracks, and they're all Latin words, so I was struggling to keep up. And medical students are really good at memorizing these things. And I really had an engineering background, so I found the Human Brain Coloring Book. And this really helped me. You color in different areas of the brain, and then you color in the word, and it really helped me memorize this. And so this is the portrait of the artist as a young man. This is my own work, my early neuroscience days from one of the early pages of this book. And let's take a look at this, because we're going to talk about the brain. And it's nice you'll have more lectures over the semester on neuroscience and how the brain works. But let's just take a look at the brain areas, kind of rudimentary. So your eye is over here in the front. So this is the front of your brain, this is the back of your brain, and this is the human brain. And so by some freak of nature and evolution for mammals, the eye information goes through here and then gets processed in your brain back here in the occipital lobe. And that's where you do a lot of your vision processing. Information goes from here down this way, and that actually is what objects are, and up this way, and that's where objects are. And also down in here, there's a lot of brain tissue devoted to how we hear things, how we remember things, and also they have this piano, so it also has to do with how we perceive music and language. Now in humans and primates, and especially humans, this big yellow area, the frontal lobe is huge, especially in humans, and that's where a lot of executive control, a lot of decision making, a lot of what we would call deep thinking happens in here and somewhat back in here. So to give you like the real quick neuroanatomy 101. I actually will be talking, I'll show you some pictures of areas down here that relay important environmental information up to here, and then it comes back down here and then drives your body to do something. All right, so that's my brief introduction to kind of how I got to where I was at. I started about 20 years ago embarking on this idea of neurorobotics. And the idea of neurorobotics, it's a mouthful, but it's trying to make a smarter robot by inspiration of the brain. So you're using the brain as inspiration for the control system of the robot. And there's two really good reasons to do that. One is you can make a smarter robot. You think of any artificial intelligence system out there or any robot out there, compared to the most simple animal, artificial systems are really dumb. But we have models out there looking at biology that are really smart. So using inspiration from neuroscience and brain science and biology to make a better robot. The other thing, and I'll get into this more in this talk, is you can use the robot as a surrogate body to test theories of how the brain works and what makes us human, right? So, and I'll go on this over and over again, but the brain needs a body, and the body acts in the environment. Or as our catchphrase was, the brain is embodied and the body is embedded in the environment. So brains don't work in a vacuum and isolation. Our brains are really tied to our body, and our body is really tied to what's going on in the world, and we act on the world and we change the world. So this kind of holistic idea gives you a way of testing brain theories in a very naturalistic way. And the rest of the talk will be showing kind of most of my work over the last 15, 20 years, and then some work by others that do this kind of stuff. So it can be called neurorobotics, like neuroscience robotics, brain-based robotics, cognitive robotics. At this stage, at the beginning, I was just a few of us, and now there's a whole community doing this. So that's the theme of the talk. Let's look at one of the very early ones. So this is in like the late 40s, early 50s, Gray Walter made what he called tortoises. And this is Gray Walter here, and this is a replica of one of his tortoises. And if you don't mind me, let me just get out of this and show you a fun video.
In a simple villa on the outskirts of Bristol lives Dr. Gray Walter, a neurologist, who makes robots as a hobby. They are small, and he doesn't dress them up to look like men. He calls them tortoises. And so cunningly have their insides been designed that they respond to the stimuli of light and touch in a completely lifelike manner. This model is named Elsie, and she sees out of a photoelectric cell which rotates above her body. When light strikes the cell, driving and steering mechanism sends her hurrying towards it. But if she brushes against any object in her path, contacts are operated that turn the...
So I'll let this play, and I'll tell you a little bit more about this. So this is late 40s, so there were really no digital computers at that time. So he designed this, all of vacuum tubes and analog circuits. And basically, this is a 2-neuron brain, you know, because it's got a neuron to respond to light and a neuron to respond when something hits it. And you look at its behavior, and it looks very realistic, you know, much better than a lot of the current lumbering large robots. And so that was a really good lesson you understand through building, and it doesn't take a complex brain to get interesting, complex behavior. And so that was a really good lesson early on that kind of inspired our field. And I do love that video. I think most of the hits on that video are me and my class that I teach this, because it's such a fun video, and it's a kind of a throwback retro video, if you will. Okay, so, you know, here I am. I'm finished my PhD. I'm trying to think of what to do next, and I have this background in real-time and embedded systems. I have this interest in neuroscience. Across the lab from where I am, they're poking animals with these wires, and have all these, they're trying to like make sure everything is just right and it's not noisy, and I go, I just don't have the patience for that, so I'm not going to do, if I'm going to be a neuroscientist, I don't want to do that. So I thought, well, given my computer background, I could maybe make models of the brain, and given my industry background, I could actually put those models on something like a robot. So that got me thinking about that, and I was about to try and do this on my own, and then I heard about this place, the Neuroscience Institute. And a job opening happened, and it's in La Jolla, California. And this institute was run by a Nobel laureate named Gerald Edelman, and he won the Nobel Prize for working out how the immune system works. And he said it was a selectionist system, in that antibodies would select whatever is foreign, and once they figure what was foreign, then they generate a whole bunch of more antibodies that are related to that, instead of having all the antibodies you could imagine for every disease. And that turned out to be how the immune system worked, and he won his Nobel Prize. And then he started turning his very brilliant brain to how does the brain work and how does consciousness work. And he came up with an interesting theory, still like on this idea of selection, and he called it neural Darwinism, in that the brain is actually, as it learns and wires up, it's selecting what's important in the world and emphasizing what's important and what's good and what's bad. And so this idea of neural Darwinism really tied the brain to the body. And so this is one of their earlier robots, and when I went to this place in the late 90s, this was in the corner, and but it was an amazing, for the time, it was just an amazing piece of engineering and work. So this robot, and they called their robot the Darwin series of automata. So this was, I think, Darwin 4. And Darwin 4 was about, half my height, and it was really slow, and it was supposed to go and sample these play blocks. And it had an artificial brain that had neurons and connections. But from what I hear, it would think for about a minute, lumber forward an inch, and then think again. And experiments would take hours, and there was one person whose job it was, because if it went past this block and didn't sample it, you lose another hour. So there's one person, apparently his job was to sit there with a broom handle and push things around it. So it was, but it was a thing of the time. So when I got there, I go, I can't work like this. One of the things I did with a really top-notch group of people is make this more like how we are, which is we don't sense, think, and act. We're also doing all these things at once. We're doing this all in parallel, and that makes a huge difference on behavior. So from that point on, we are able to get systems that work and act a little bit more like a real animal. Okay, so before I get into one of my first robot experiments, I have to remind you of Psychology 101, right? So hopefully you've heard of Pavlov's dog and remember the idea of classical conditioning, but this is a nice picture of it. So a dog is about to get food, smells the food, and starts salivating, right? So the stimulus, the unconditioned stimulus, is the food, because that'll always cause this reflex of salivation, and the unconditioned response is to salivate and be excited about getting some food. And then if you pair that, or you start with a neutral stimulus like a bell, or in this case a whistle, it means nothing to the dog. But if just before the dog smells the food, you ring the bell or blow the whistle, the dog starts learning that there's an association there. And this is called conditioning. So then this unconditioned salivation, if I just blow the whistle alone after conditioning, then just blowing the whistle will cause the dog to salivate, because it has this expectation of getting food. And that's some experimental psychology. There's a whole body of work still going on different ways of doing conditioning. So the question we ask, well, can you do that kind of psychological conditioning in a robot? So we designed a robot. I think this was called Darwin 7. And the robot had an artificial brain. So each little box has a bunch of neurons, artificial neurons. If anyone wants to go in the math, I can talk about that later on. But each box has a bunch of neurons, and neurons for hearing, neurons for seeing, because it's got a camera and it's got microphones for ears. And then these streams, just like in the real brain, further and further process information from very raw pixels to edges and shapes to this point where down here it's actually recognizing full objects. Now, Darwin 7 had a way of tasting things, and its taste buds were in its fingers. So it has taste buds in this gripper right here. And what it tastes is conductivity of metal. So just like, well, with a kid, if you ask them what food do they really like, they'll say, like chocolate or cereal, and then what food do you really don't like, and reflexively it would be like, Brussels sprouts or something like that. So it's kind of a reflexive response, an innate response. And so this guy's innate response was highly conductive metal was good tasting, and weakly conductive metal was bad tasting. So it didn't know which blocks were predictive of good taste and which blocks were predictive of bad taste. It had to learn that. So let me show you a video. Before I start the video, this will be Darwin 7 moving around the world. This is just parts of its brain. Each little pixel is a neuron in its artificial brain. The brighter the pixel, the more active that neuron is. This is an early visual area. And so it's kind of what you see is what you get. The brain in the early visual area has a topographic map, so this is kind of accurate. And then this is a higher order visual area that will start to learn categories for different objects. And I won't show you the auditory because it's kind of noisy, but this would be its auditory area. And over here is its value area. And I forget which side. I think the left side is bad tasting and the right side is good tasting. So let me roll this. This is the first time he tastes a striped block. it's good tasting, so that gives him positive feedback, positive value. Now it's approaching a spotted block. That's something that's bad tasting, but he doesn't know it yet. So he'll still pick it up. And this is bad tasting, so his job is to remember that stripes are predictive of good tasting and spots are predictive of bad tasting. And just like Pavlov's dog, we let it experience this over and over again, this pairing. And it took about the same time as a dog or a rat would to learn this task. Before I run this video, I want to show you this. So here's a block, and it's angled. So it could be vertical, it could be horizontal. It's really not in its paw. So it's not how it usually sees it. But it already, before it even tastes this block, has a good representation of this category and is also predicting it's going to taste good. It's like that dog. It already knows that if I make this action, it's going to taste good. And actually being able to recognize something that's in a different orientation and a different position is a really hard problem in computer vision. But we solve this just because we treat vision just as like a video stream of life. And so we're always putting things together. And because it's roaming around the world, it's naturally building up these, what we call in computer vision, invariant object recognition. So let me run this. So this is good tasting, so he will pick it up. And this is one that's bad tasting. He's learned that it's bad tasting, so he'll look at it, but he knows it's bad tasting, so he will not pick it up and he'll back away. And he'll do that over and over again. But he does it very well. And you would do it the same for if it was these blocks could also make noise, and so he would also learn one particular noise was predictive of good value, one predictive noise was predictive of bad value. So this is really I think for me, a landmark study to show that, yes, machines could learn, and yes, machines could do the type of behavior that we attribute to animals with cognition. Now, I'm not the only one that did this. It's a growing community. I wanted to show you some of the other types of ways of studying in neurorobotics. One is being more, we call it biomimetics, so more mimicking biology. So this group from England wanted to look at how whiskers work in a rat. And so I love this video. So rats actively whisk. And doesn't that look, some people are creeped out, but I think it's really cute, and it looks like a really curious dog. And when I talked to these people, I thought it was fascinating because, you know, a rat is really small, and a hair cell, hair coming out of a rat or a cat vibrates when it hits something. And that's really important. So when they scaled this up to a dog size, they couldn't use hair. It wouldn't work. So a lot of the work to figure out how to do this was figure out materials. And they finally found broom bristles that had the right kind of response and vibration so that they can mimic what the rat does scaled up. And let me jump out. I know, he's cute. Oops. Let me jump out. I want to show you one more YouTube video. Because I think this is really interesting too. This is a group, I think, from Switzerland. Here we go. They made a salamander robot. Now, why did you make a salamander robot? Because it's amphibious, and it was a good way to study how animals went from sea to land. And I think that robot's really cool, but I want to explain there's a lot going on there. I'll run it again, but what they found was it wasn't just the brain saying, swim now, walk later. The brain actually was not controlling, the body was controlling the brain, which I think is a very important point. So if you watch closely, as the water gets shallow, the feet not only hit the bottom, but the turbulence is different. And so the body naturally automatically goes from a swimming gait or swimming kind of eel-like behavior to a walking gait. So let me show that again. It's very subtle, but that's what's going on in this robot. So it's swimming, it's getting shallower, the feet start to rotate as it's shallow, it hasn't even hit the ground yet, and then it goes into the walking gait. Yeah, so I think that's really cool, and that's a lesson that is important for us roboticists and us philosophers and us thinking about what makes us human. The body is really doing a lot of intelligent behavior, and the body is shaping the way we think, which is the title of a really interesting book that we'll come back to. Okay, another way of looking at building a smarter robot is looking at genetics. So again, this isn't work that I do. Actually, it is work that I do now, but the thing I'll show you is work done by another colleague named Dario Floriano. And so like in genetics, you can do this artificially, where you have a bunch of robots, you select which one was fittest, you mate it with other robots, if you will. I'll explain what I mean by that, but bear with me. You make a new population of robots from the smartest ones, and you do that over and over again, and then you eventually get a smarter robot. Now, when I say mate, in this case, there's a genome that's describing how its brain network is wired up. And so the better robots, they only had one robot, but they had 10, I forget, somewhere between, I'd say 10 and 100 brains, and they would pick the top, let's say it's 100, because it's usually a number, and then they pick the top 10, and then they would shake around how those networks are wired up and generate another 100 robots and keep doing that. And the task was simple, but the idea is really complex and interesting. So here's the robot at the very beginning, and the fitness for this robot is not to bump into things and how much distance it can cover in a period of time. So at the beginning, there's no knowledge yet, so it's just not doing much of anything. After a few generations, it's still kind of not doing much. About now, it actually is learning, because it has sensors in the front, around its body. It's learning to respond to sensors. So when that person put the hand in front, it actually moved. Now, it's actually, by 50 generations, they've developed a robot that can navigate around this spot without hitting anything and move at a nice pace. And what was interesting to me is, at the beginning, there are just sensors around this ring of the robot. It had no idea of front and back, but the better sensors there were better sensors on one side and sensors that weren't as good or weren't as many on the another side. And so it learned a front and back. And so it's moving to where it has the better sensors. So I thought that was fascinating, that is kind of an emergence of intelligent behavior and an emergence of understanding what the best way of the body pattern or layout of sensors. And if you think about us, and I like to use this example, if you think about us, we have hands, and most of the sensors in our hands are on the fingertips, because that's where we touch things, and that's where we reach things. And on the back of my hand, oops, sorry about that, the back of my hand, there's not as many sensors. Why? Because that would be a waste of sensors, because usually I'm manipulating things with the fingertips. This is the same idea. Okay, so these are some kind of simple robot tricks at this stage. And then we started thinking about, what about some more cognitive kind of things that make us human. And one thing is our memories, right? So we have what's known in textbooks as episodic memory. So that's putting together the what, when, and where of events. Where were you when 9/11 happened? Which I can't use that phrase anymore with my students, because some of them weren't born then, which just blew my mind, because I said that in class the other day. I was like, oh, you were nowhere at that point. So I have to think of a new analogy. But anyway, you get the idea. So it's not only is it episode, but it's autobiographical, right? So how do we build these memories? And an important part of these memories is there's an area of the brain called the hippocampus that's critical to forming these memories. And over time, these memories get put in other parts of the brain and get stored in humans, on the order of decades to a lifetime, all right? But the hippocampus really is on a much shorter time scale, on the order of minutes. So how does that happen? And so, our human brain is huge, but it's very similar to in its layout to a rat brain. So a lot of the work has been done for memory with rats. And rats are really good navigators. And there's a gold standard test called the Morris Water Maze. And let me start this. So this is day one. The researcher puts a rat in a tank of water. Rats are very good at swimming, but they don't like being in the water. And I don't know if you can see it, but there's this faint area here. That's a little platform that's hidden underneath. The rat can't see it because the water is opaque. It's milky white. So the rat is really exploring, building up knowledge about its world and its place, but it really doesn't know how to get out of this situation until by random chance it stumbles on this spot. And see, it's kind of random, but eventually it will get there. So about 5 days later, put the same rat in the same tank of water. He's so close. All right, so look on the right. This is the same, this is the rat again, but it's after 5 days of this, and watch the difference. Really goal-directed behavior. So it goes there, it goes near it, takes a little side turn. Oh, yeah, no, cheering on the rat. Here he comes. And now he's happy, right? So he's on the spot. And this guy did eventually find it, okay? Why do I say it's a gold standard? Morris was actually a person, Richard Morris, and he came up with this paradigm and realized if you didn't have a hippocampus, which you can take out in rats, and sometimes it gets injured in us humans, they could not perform this task. Because it is an episode in the rat's life, right? It needs to know the what, when, and where things are. So this was a gold standard. We wanted to do it with a robot, and we didn't want to build a submarine, so we had to figure out a dry way of doing this. That was one challenge. And the circuitry for how the brain interacts with the hippocampus is very complicated. I won't go into the details, but this may have been the most complicated network I ever made. So again, it has, each one of these little bubbles has a whole bunch of neurons, artificial neurons, that fire or become more active. And it's got a what stream, a where stream, so what things are and where things are in its world. It's got an internal compass, which we do too. We have our inner ear gives us knowledge about where our head is pointing. It's not tied to true north, but if you go in a room, and I actually recorded from your brain, and the room was familiar to you, you'd have neurons that would be pointing like this direction, neurons that would be pointing this direction. So it gives you, your inner ear gives you a lot of information of where you're heading. They call it head direction. So it had a head direction system. And I won't go into how this hippocampus, there's some very detailed circuitry. We had to work this all out, and I worked very closely with a neuroscientist who studies this area of the brain and gave me a lot of information about details. So the task for this guy is similar to the rat in that water maze, is roam around this room. There's a spot we call a hidden platform that's the same color as the floor that it can't see, but it can feel. All right, it has a little sensor on the bottom of the robot that can feel when basically it's on this spot because it has it's a different piece of construction paper from the floor. So here it is in action. This is day one in the life of the robot. So like the rat, it's wandering around, it's building up information about where things are. So it's building up information about place. But it is kind of like that rat on day one, just wandering around randomly. So here's day 8 in the life of my robot. Now it's looking more purposeful. It's actually searching for the goal, and it's heading to the spot over there, which is where its hidden platform, and it gets a nice reward. When it gets there, it goes right past it, which really bothered me at first, and now it's getting that reward, all right? So like the rat, we try to run this multiple times from multiple places, multiple starting points. So we know that it's not just a series of left and right turns, okay? So this is the same robot or same robot subject. And again, it should be going right to that spot, but come on, no. And there we go. So I was really curious why it was doing this. I was kind of frustrated that I wasn't going straight to the spot. And then when we thought about it, we realized, well, you know, that's not a bad strategy. If you just go find the blue wall and bounce off of it, you'll actually get really close to the reward spot. So this robot subject, if you will, learned that and made a habit out of that. And it was a good, it was actually a very good strategy. So when I say robot subject, so we had one robot, but we could make, each one of these arrows is how the brains are connected, and each one of these arrows represents thousands and thousands of connections, just like in the real brain. And there's, I hate to get into math, but there's a probability distribution between how this is connected to here. So there's some variation. So if we just roll the dice and generate another brain, it'll have this structure, but it'll have, at the very micro details, it'll have a lot of differences. Just like, you know, my brain is very much the same as your brain, but if you look at the details on the microscope, it'll be different. And the other thing is the real world is extremely noisy and complex. So no two robots that I've ever made have had the exact same experience, and it's learning from experience. Why am I going that long thing? So we ran this 10 times. So just like a lab rat, we ran 10 subjects. And some of them did the blue wall. Some went straight, like I was expecting, onto the spot. Some actually had a red wall strategy. So each one of these subjects had its own little personality and its own way of solving the problem. We also did a trick where you remove this platform and just see where does it search, okay? They do this with rats too. And some robots would search around here, go, hey, I don't have a reward anymore, and then just go exploring around. Other robots were extremely perseverant and would constantly be like, where is it, where is it, where is it? So you see these personalities emerge just because of the interaction of the brain and its body in the real world. And that, even in this controlled environment, that complexity really leads to different solutions and kind of drives the point that it's not just nature, it's nature and nurture. Okay. So where are we? This is still my work before UC Irvine. And then when I started the lab, the Carl lab in UC Irvine, I got interested in value and like how do we build value or value systems? How do we tell the difference between good and bad? And how does the brain do that? And so I started reading and talking to people about where's the brain, encode value. And I realized that through talking to all these people and doing a lot of reading, that there's these areas of the brain called neuromodulatory systems that respond to value and have very specific chemicals. So I hate to give you neuroscience lessons, but this area here is the substantia nigra and ventral tegmental area. This is where the brain produces dopamine. So you may have heard of dopamine. It's a chemical signal or neurotransmitter for the brain that signals reward and pleasure, okay? And this small area below the brain, I'm below the neocortex or cortex, projects all over the brain. So it's sending a reward signal all over the brain, okay? And dopamine, if drugs of addiction and entertainment drugs also tap into the dopamine system and can trick your brain to always being reward seeking. But when it's working properly, this area drives how rewarding or pleasurable something is, how to predict what actions will lead to something rewarding or good, and also drives a little bit of let's seek out some new things that might be potentially rewarding. Now on the right is the serotonin system, and the area in the midbrain, or the pons of the brain, called the raphe nucleus, is where serotonin is generated for the rest of the brain and the body. And serotonin actually, just like the dopamine, comes from here and projects all over the brain. And there's also arrows going down because it actually is very important for movement too. Serotonin you might have heard of. Serotonin is a very difficult thing to figure out what it does, but obviously it affects mood. Drugs that boost serotonin levels are used to treat depression. Serotonin seems to be not necessarily for punishment, but for how much risk you're willing to take, how conservative you'll be, or how much you want to stay out of harm's way. And you can imagine a person who's depressed might become extremely withdrawn and want to just stay in a corner and stay out of harm's way all the time without doing reward seeking. So there's kind of a yin and a yang opponency between these two systems. All right, given all that, say, well, can you model that in a robot, and can the robot learn different values like that. So this is the original Carl, Carl 1, if you will, that we did about a year or two after I started the lab. Carl plays in a disco floor, so it'll flash different colors. And this floor is amazing. It's interactive. And underneath the floor, it's sending signals. So a green panel would send a signal that tells the robot this is rewarding. A red panel will send a signal to the robot saying that this is something harmful. And any other color would send a signal that's just purely neutral. Now, here's, again, just like before, these are different brain areas. Each little pixel is a neuron, and the brighter it flashes, the more active. And remember, I talked about the ventral tegmental area, that's its dopaminergic system, and the raphe nucleus, that's its serotonergic system. So let me run this. So he sees the spot, it goes from green to red, and quickly that serotonin system says, hey, that's harmful, and that's as close as he'll get. And he watches it very warily. Then it turns green and goes, hey, that might be potentially good. And so then the dopaminergic system immediately comes on, and he'll just stay there and enjoy that reward as long as it stays that color. All right? So at a neuroscience level, this really taught us a lot about how these systems can really react very fast to cause you to switch behaviors quickly and then cause long-lasting learning effects to remember. Now it turns a neutral color, doesn't pay attention to this at all. I thought that was a really nice demonstration. So then this is Carl Roomba. And Carl Roomba is doing what a mouse would do if you put it in a novel environment. It's hovering around the edges of the room, and then the Roomba's charging station is this corner, so now it's seeking a hideaway, its nest, if you will. Now, Carl Roomba realizes that, hey, this room is pretty safe. Why don't I explore? And so, like a mouse, it'll start making movements to the middle of the room and exploring novel objects. Okay? So this is another gold standard test for anxiety models. So you can, with mice, you can change certain things in the mouse and see how long it spends on the edges or near its nest. If it spends too much time on the edges in its nest, then that mouse is very anxious. If it spends too much time going in the middle, then that mouse is overly curious, and so it's aberrant behavior. So we would do this with our robot. And we could turn its dopamine levels up very high, and then it would become obsessive compulsive and just constantly be like going, hey, what is that? What is that? What is that? Then we turned its serotonin levels very low. Very low. We turned the serotonin levels very low, and it wouldn't come out of hiding. It would go over to this spot and just cower in the corner. So it was actually an interesting model of how these dynamics between these systems actually lead to the balance between being overly curious and being overly cautious. And then value can be used to predict things. And we build up kind of models of the world and models of intention. So this is one of our later works. And this robot here has a value model, but it also has, it builds up predictions of what actions it'll do to get this food and what actions it'll do to hide from this predator robot. And then over here is its hiding space and nest. And if it's in this hiding space, this predator robot can't get there, can't see it. So he realizes he's getting too close to this predator robot, so he goes over here, and now he's in his hiding spot. He waits till the predator robot has its back turned, and then runs to that purple spot where it gets its food. I know it's slow, but I wanted to play that out. And this robot, this is kind of an interesting idea for us, because not only does the robot have idea of what actions it can take based on where food is, where the predator is, that'll lead it to good value and not lead it to getting caught, it also builds up a model of what are the intentions of the predator robot, all right? So it really thinks through, if I move here, like the robot, the predator will move there, and if I move this way, the predator will move. So it builds up what we call a theory of mind. So it actually has the ability to put itself in the other agent or other robot's shoes. And so that's a really big step, I think, of taking value and using that to actually start to look at things that are more cognitive. All right, so this is kind of a body of work that since I went to UC Irvine had done, and I was going to go to a conference at the International Electronics and Electrical Engineering Society, IEEE, and they heard about the work we were doing, and a journalist called me up and wanted to interview me. And so I told him about this work. And a friend of mine called me up, what did you say to that journalist? And I go, what? We had a very nice conversation. He goes, well, Jeff Krichmar, professor of cognitive science at University of California, is experimenting with building neurotic robots. I was like, what the heck? And at our university, we have a very good media department. So once it gets, this was a new experience for me. I've given interviews before, but once it gets out in the media, other people pick up, it's kind of like that word game you play as a child. They pick up that story and then put it in their paper. So for 2 weeks it got on the wire, and every day the university has these web crawlers that tracks when the word UC Irvine happens, and then we'll email it to me because it says Jeff Krichmar. So I'm getting emails daily for 2 weeks like, what's this other headline like, I can't read it from here, but I think it says researchers making neurotic robots that like humans that fail, and other things. Programming robots to be neurotic. And I was like, well, really, what I told him was it's neurorobotic, not neurotic. So he dropped a syllable, made headlines. Now, I give the person credit. The robots, especially that one where I gave it the obsessive compulsive disorder or anxiety disorder was kind of neurotic, but yeah. So that was sort of a fun little experience. People say, oh, you should correct them, but I was kind of enjoying it for like 2 weeks of fame. All right, so I'm going to switch gears a little bit. I'm going to talk about some of the practical aspects that are coming out from this technology or these ideas. And one gets to my computer science background. I've been working with people who build computers, hardware engineers, and they're trying to build a computer that's more like the brain. And they call themselves neuromorphic engineers. And the idea is, at this point, at this stage in computers, they're about as good as they're going to get. There's a bunch of other things, but the raw computation, the amount of transistors and elements you can fit on a piece of silicon is pretty much where we can't fit anymore. So we've known that in the computer science community for a while, and they're looking at alternative ways of doing computing. And so some of these engineers have turned to the brain. And because the brain just does everything in parallel, I know probably not everyone knows computer science, but when you're looking at the specifications for a computer, it talks about, the clock runs at 3 gigahertz or something like that. So there's a clock going very fast. Our brain doesn't have a clock like that. So our brain just works when something happens, it responds to it. So they use those ideas, and the idea that when I talked about neuron activity, I didn't really get into what an action potential is, but when a neuron tries to send a signal to another neuron, it does, watch my finger, it does what's called an action potential or spike. So it goes up rapidly and then goes down. And then between the up and down, it's hovering, just collecting information. From an energy standpoint, that's really efficient, because the only time it really expends energy is in that 1 millisecond when it's going up and down. So the hardware engineers go, what if the computing elements just did that same thing, kind of would spike with an event, and then the rest of the computer just sits there not spending energy till it gets a message and says, oh, now I have to wake up and do my spike. So to make a long story longer, the computer I'm running right here, my laptop, is probably taking close to 1 kilowatt of power. The brain is doing all this stuff that I'm doing with about 20 watts of power. So we're amazingly efficient. 20 watts, that's like your refrigerator light. So we're amazingly efficient. So these chips, one's made by IBM, and now Intel, we worked with them, has made a chip. These chips are extremely efficient. Not as efficient as the brain, but they're operating on hundreds of watts, okay? And that's a big thing of the future. Now, I got interested in working with these people because of the robotics. You can imagine for robotics, having a robot that you want to learn over a lifetime, you can put it, if it doesn't draw much power, it can run continuously, because that's the bane of robotics, is how do you keep these things powered? So, I have to make sure there's no sound on that. I'll explain why. So there's a wonderful meeting in Colorado, in Telluride, Colorado, and I had the opportunity to go a few years ago. And it's a gathering of all these nerds. And so our group went down. That's one of my students, Tiffany Hugh. Our group went down to work, brought a bunch of robots and some of our ideas. And other people came, and the rest of the people are from IBM. And IBM said, hey, we have this cool new chip that we've been developing, and it can run artificial neural networks and take very little power. So Telluride is up in the Colorado Rockies. It's all these really beautiful mountain trails. So we drove our robot around and drove it on the mountain trails and collected how the person was driving it. Then we used that information to train their neural network to actually be a better driver. And then the idea was, all right, now we have this neural network on their chip, which is like one of the first they made, so it's worth millions, because I was very nervous. And it's the last, getting to the end of the conference, go, let's test it out on your robot on the mountain trail. So these guys grabbed their chip, and this guy in the orange, I remember this very well, he goes, I designed this chip. It's never run off a battery, but I think if I just put this little jumper cable here, it should work with a battery, but I hope it doesn't blow up. And I'm thinking, like, this is a multi-million-dollar chip. And so he put it on there. We hooked it up to the robot. It's literally strapped to the back of our robot. Oh, oops. Let me get back. Sorry. Since we were in Colorado, this robot became Carlo-Rado. That's our Carl robot. So this was the first time we tested it on a mountain trail. So let me, sorry. Let's do it this way. There it goes. You don't get a feeling for how steep and rocky this trail is. It really is. And there's like a 100-foot drop off to the left of the robot with this multi-million-dollar chip. So there was we attached a rope to the back of the robot in case it veered off. But luckily, the robot stayed on there. And I had to turn off the sound because the engineers were so excited. There's a lot of swearing and cussing in a good way. But what's amazing to me was that this robot was made with off-the-shelf parts, and we used a small battery that you'd use for like a remote control car. So the battery on the robot was controlling the robot, what it was doing, and also powering this computer running a full neural network for self-driving. So that really told me this is the future, because a lot of what's going to happen is computing is going to go what they say out to the edge, where you can have small computers like sensing environment, doing a bunch of things, and they have to run for months. And so you can't, and they might be very far from a power source. So this is actually, not only is it going to get us out of this bind that these computers can't get faster, but I think it's going to bring up some really interesting applications in the future. Another application that we do that happened over the years was, with all these smarter robots, we got interested and people got interested in us. Well, can you use these smart robots, to help people? I was like, what a novel thought. And I'll tell a story how we got into this, but one area is children with neurodevelopmental disorders, and just autism for one thing is the number of people with autism spectrum disorder or number of children is just growing and growing, and it's really hard on families, it's really hard on healthcare systems, and it's really just tragic seeing them. And one thing about robots with children with these neurodevelopmental diseases is they seem to respond really well to robots. People are too intimidating for them. So we're thinking, well, maybe robots could be a bridge to having them learn how to properly interact socially. All right, so how did I get involved in this? It was a story worth telling just a little bit. We really weren't thinking in this way. We were thinking, well, I want to make a robot. I told my engineers and my students, I want a robot that you could touch. You know, I like a cat. You know, if I pet my cat from head to tail, it's happy. But if I pet my cat from tail to head, it's going to scratch or bite me, right? So there's some sort of value to the way you touch it. And if I'm too harsh, the cat will get upset, you know, and also the cat has a body plan. You know, I'm using my cat as an example, but you could think of anything. There's certain areas that you touch it and it knows where you touched it. So it has a sort of body awareness. You know, can we make a robot that has that? So we started looking into artificial skin, and it just isn't there yet. You know, because we're talking about like a touch screen that covers a very large curved surface that you can pet. Well, around the time we were building this, one of my engineers who was very clever, named Liam Bucci, said, well, you know, let me buy a bunch of BlackBerry phones. They're not doing very well. And he ripped out the trackball of the BlackBerry phones. And this made the perfect sensor, right? Because the little trackball can give you directional information and in any direction. And also, for our standpoint, when you rub your finger across this, it gives, in electronic terms, a square wave, and that looks just like a neuron spike. So it's like the perfect biomimetic sensor. So then we built a robot. This was our first robot. This robot was originally called Carl's Jr. because it was well, it's a long story, but just the brief part of the story is one of my students that worked with this wanted to make a startup business, and the people, the lawyers and the business plan people said, you can't call Carl's Jr., you'll get a lawsuit. I thought it would be a positive thing. So now it became called Carbo, Caretaker Robot. So here's Carbo here. That's my hand rubbing it. And Carbo responds, you can't really see it very well, but if you look over here, it responds with lights. And I should say, as soon as we got this thing working, kids just gravitated. So we get a lot of kids coming through our lab just to visit. And they were mesmerized just by petting this. So we said, well, can we make a series of games to teach children, you know, how to interact properly based on touch? And it turns out children with autism and ADHD handle things differently than typically developed children. So we've been working with this robot on the top and this original robot on the bottom with a lot of people, a lot of children with autism. So this is a study at UCSD that we wound up, and then it's now in Vanderbilt University. What's fascinating about me, all these children have autism. So that first child was very interactive, but this child has sensory motor issues. And actually, he looked up there with that caretaker, which was a breakthrough for him.
Tien, excellent job.
So this is very promising. Already we can tell that children that have these types of disorders really want to interact with it. And that's a good thing, because then they want to come in to see the robot, and then they work with a therapist. And also, I'm hoping this current study at Vanderbilt that will actually show that there's long-term effects, that what they do with a robot will transfer to how they play with other children and adults. Another way we've gotten into this field is, again, serendipitously, we were approached by Toyota. They have a brand new robot. Let me turn that off. They have a brand new robot called the Human Support Robot that was designed to help healthcare and elderly, and also people who were stuck in a hospital bed. But I was working with someone in the School of Education, and they said, we have these children, they're homebound, they have terminal illnesses. And it used to be that they didn't have a very long life, but now with medicine, they're actually living a long time and getting all the way to college. But now they're left out of school because, you know, their immune systems are compromised, so they can't go in, but they feel left out. They want to interact with their children. So they want a robot that actually makes them feel like they're in the classroom. So we, over the summer, converted our lab from a robot lab into a classroom. And what happens is children will come in on the robot and learn how the robot works, and then take a Spanish class or a Mandarin class with one of our people, and then tell us if this actually is a good experience, and can they interact with the teacher? Can they interact with classmates? So this is another area that we're moving into, and we're using some of our ideas from neuroscience to make the interaction more natural. All right, so let me kind of give some final thoughts and get towards wrapping up. So these days, artificial intelligence is really popular, more popular than ever. I've been in this field for a while, and you can see there's a lot of hype and buzz. And we have artificial systems that can recognize objects. They can even, it's kind of blurry, but they can even give descriptions of what's going on in the scene. We have artificial systems that can play games that we kind of attribute to intelligence. So for a while we've had artificial systems that can beat the master chess player, but one standard was the game of Go. I don't really know the game of Go except as using these little tiles, but apparently that's much more difficult than chess, and no artificial system could beat a champion Go player until very recently this system came out that they called AlphaGo that could beat the champion Korean Go player. But I think at this point, even though there's a lot of buzz, AI is way overhyped. And so there's some limitations with this approach, and it works in a limited domain. You have to train it to do one task. If it has to do another task, it has to be completely trained from scratch. That's not how we do things. And there's certain things we take for granted in intelligence that these systems can't do, that we take for granted, but it's really a part of our intelligence. And I would say, like, if I was playing AlphaGo, I could beat it in one step. Just pull the plug on it, right? I mean, we're all self-sufficient. We're able to get around. We can provide our own energy. Any artificial system at this stage needs an external power source, needs a whole army of programmers to keep it going, needs a whole army of computer systems, analysts, people to keep the robots going. So I think that all is part of our intelligence, and I think that's being overlooked. Now, how many of you know what a Palm Pilot is? Or remember a Palm Pilot? Yeah. So the guy who invented the Palm Pilot came out before smartphones, but it really was the first kind of trend towards smartphones. And the person that was the CEO of Palm Pilot was Jeff Hawkins. And at some point, he realized the writing was on the wall, sold Palm Pilot off, made a lot of money. But it turns out Hawkins was a closet neuroscientist. And so some of the best ideas in neuroscience, I think, are coming from this person. And he basically said the same thing, that there's certain limitations of the artificial systems, and to overcome those limitations, we should turn to the brain. And so he said that one of them was learning, he called learning by rewiring. So that means that we can learn something very quickly. We can keep that learning over a lifetime. We learn continuously, and we don't have to, every time we learn something, we don't forget everything else we've done. Artificial systems can't do that. We do that very naturally. Sparse representations, what does that mean? That means that the brain is really energetic. So when I'm representing things in my brain, like the images of you and other things in my world, I'm doing it with the least amount of energy possible. So that's what we mean by sparse. Embodiment, I've kind of been showing you one after another how the interaction between your sensory system, your motor system, how you sense things, how you act on things is dynamic and interactive and multitask in parallel. And then I added a couple more, the value systems, which I talked about, and being able to predict value, so using your past experience to be more successful. And I think we need to take a holistic view to how we build artificial systems. That, neuroscientists, cognitive science really focus like on one brain area at a time, but the brain is highly interactive, and the brain is constantly working in conjunction with the body and in the world. And roboticists are often trying to make a better walking robot or a better reaching robot, and not thinking as much as how does the brain actually control that? And those things go hand in hand. In fact, the body does a lot of the heavy lifting and computation. So this really nice book that I use in my class by Rolf Pfeiffer and Josh Bungard called How the Body Shapes the Way We Think has this idea of morphological computation. So certain brain processes that we do are freed up by the body just being intelligent. So if you watch, wait for it, here he comes. Where is he? Wait, there he is. I love this robot. So this is a group at Cornell, a bunch of engineers, and they just wanted to make a walking robot that used the least amount of energy. And so they actually designed the body so that it would take advantage of things that we take for granted, like gravity and friction, right? So if you think about walking, it's kind of a controlled fall. You push off with one foot, but then you fall on the other. So you're saving all that energy. Most roboticists are trying to, like every millisecond, trying to figure out what the right angle for the right, each foot and each leg should be. Whereas this guy was just doing a controlled fall. And every time I met with the person that designed this, he said every time we reduced the energy to its minimum, then we got something that actually looked very natural in the way it moved around. So this robot on a single battery, I think went, I remember how many days and kilometers on a single battery before it ran out of juice. And then below, just looking at other animals in the world, animals, and we do too, but we take it for granted, take advantage of the world around us. So soaring birds actually look for, or just naturally find air plumes that save them energy and use those to their advantage. And actually winged insects and many birds, when they push their wings down, they're not only giving themselves thrust, they're causing a vortex of air behind them, which is giving them a push. So they're changing the environment to their advantage. And that's what this idea of morphological computation does. So your body is doing a lot of intelligent behavior, and that leaves your brain to do some more things that brains are good at, like adapting and predicting outcomes. All right, so let's wrap up. Want to leave you with a thought that robots are our friends. I collect, and people give me lots of little toy robots. So, but seriously, let's talk about some of the developments coming out of this field, which I think robots that are much smarter will really help. One is self-driving cars. Technology that's just about there right now, and that'll release us from having to pay attention on the road. We can do other things, like this woman is reading a magazine. It should reduce traffic congestion and should make driving much safer. So that's coming down the road, if you will. Another area that I think is in the near future where robots can really help is disaster relief. So after the tsunami in Japan and the plant in Fukushima, a nuclear plant, there was a radiation spill. We didn't have good enough robot technology to go into this high radiation area and close the valve, so a person had to do that. So, I mean, that's a situation you'd much rather have a robot that wouldn't be harmed by that radiation go and do that. Exploration. So, Mars, some of the best things we know about Mars come from robots that are exploring. So there are a lot of distant planets and places that are hard to reach, like the bottom of the ocean, where it would be really good to have smart robots that could learn about these things, or in the case of some other planets, go to these planets and set them up so that humans can habitat them. And then I think one of the big areas that really started in Asia and now is finally gaining traction in this country is healthcare and assistance. So a lot of the robotics that I'm seeing now, and now in this country too, are there to help healthcare. For example, nurses have to lift people up and put them, and nurses over time get really bad back problems, so it can be debilitating, and then they can't work anymore. So robots are helping assist with that. There's a whole work right now, it's kind of poor in its behavior, but home assistants like Alexa and other things are like sending you recipes or making restaurant reservations for you. But imagine if that got better, that you had a true assistant that could help around the house or do things for you when you're busy. Okay, so I think in general, I think the future looks very bright. All right, so let me tell you the people who really did the work. This was my group at the Neuroscience Institute just a couple years before I left, and all the different robots. This was the Darwin robots, and this was my original lab when we got there. That's the original Carl. So a really incredible group of people It was a small group with only one robot, and this is the lab as it is now. Many more robots, many more wonderful people that do all the work and come up with all the great ideas. So the future, I think, looks bright, but I do think there are limitations, and I hope I made this message that twofold, that one, to get really smart robots, you really should turn to the brain because it's what we call an existence proof. We know that organisms with brains are very smart, their behavior is flexible, complex, intelligent, and so this might be a way to make intelligent robots or intelligent artificial systems. And then the flip side is there's so much we don't know about the brain, and the brain is very closely tied to the body and the environment. It's very hard to study that in real situations, so using robots as a test subject with artificial brains might be a very good way of learning more about how the brain works and how it leads to interesting behavior. All right, and I will stop there. Thank you for your attention.
Thank you very much, Dr. Krichmar. I was so worried that Arnold Schwarzenegger was going to come in and take over the world when I walked in here, and now I'm a little more comforted that it'll be at least after I die that he will come in and take over. So thank you very much for that. We want to open the floor for questions and answers. Questions and comments on whatever you want to say. There's some microphones that are going to be going around. They're obviously out there somewhere. You know, some robot handled that one. No, but if you would, if you'd like to say something, ask a question, please raise your hand and someone will come to you with a microphone. I see a hand back in the back. Start right there.
Hi, is this on?
Yeah, it's on.
Speaking of Arnold Schwarzenegger, that was going to be one of my questions, which you sort of answered, answered toward the end. How plausible is it that in the future there could be such a thing as Skynet and intelligent robots taking over? And also, is there any possibility of an intelligent android such as we saw in Mr. Data in Star Trek: The Next Generation?
Right.
Thank you.
Good question. I often get the Skynet question. First of all, we are.
Can't hear you.
Oh, all right, we'll use this.
Yeah, that's fine.
Okay. Yeah, that's a good question, and I often get that. One issue I have is and I actually went to a meeting with people at Hollywood. So one issue I have is Hollywood does play to our fears, and so you have the Terminator, you have Ex Machina, and movies like that, and Eastern societies is really embraced robots, so it's different. They realized early on that robots could be a technology that's good. Now, with any technology, there's good and bad. So I mean, it's up to us as engineers and up to us as society to make sure that we put some brakes on, put some controls on them so that they're safe to operate, and then they're used for good things. I do think the Terminator Skynet scenario is we're several lifetimes away from that. I mean, we have such a long way to go. If you look at the current state-of-the-art robots, they are really simplistic in what they can do. That's something that's not going to happen for a while, but it is a concern. My main concern these days, though, is with weaponizing drones. So having those, that's what I'm saying. There's a wonderful science fiction writer, Isaac Asimov, who years ago came up with the 3 laws, say, for robotics. And the first law was a robot shouldn't harm another. So with drones, we violated that. So that is a concern. I think as a society, we have to make sure that we have brakes on that and fail-safes for that. Yeah.
Right back in the back there. Right
Is it likely that someday intelligent robots will be able to design more intelligent robots?
Yeah, that's a good question. And there are people, it's still very rudimentary, but there are people that have really simple, like building block robots that can make a copy of themselves. At this point, it's really, a lot of robots are used for manufacturing, but to make a robot make itself would be very, very difficult. There's a lot of pieces involved, a lot of people still have to get involved, and I think part of us is putting my engineering hat and I want to be in control of the design. So I would want to design the robot for my uses. So I wouldn't want the robots to be making themselves unless I actually had very much control over the design of what it was going to do.
Down here.
Do you hear me?
There.
I have a question. In today's environment where you're already getting ready for self-driving cars, is emotion programmed at all into the value systems that are being used today?
Yes and no. We're at an early stage, but that is something that people with not as much, I think, self-driving cars, but looking at how people are, in education or out in the field, like looking at their emotions to see how they're actually understanding their emotions so they can give the right response. So there's a group at USC that has, I think it's called the Sensei bot, but anyway, it's a artificial psychotherapist, and so it's trying to read, it's looking at facial expressions, tone of voice, all those things, trying to figure out the emotion, so it's actually being able to talk a person through its problems. So that's a big thing. So these value systems, I think, do lead to what we call emotion, whatever that is, and it's very important for our survival. And then, so that's sort of where I come from, but there's a whole bunch of people there trying to look at people and try and understand what their emotions are, because that's a very important cue of how we interact. So if you want more natural interaction, you really have to understand emotions.
Up in the back.
Will this be able to work in the reverse with what you're learning so that the chips can then be placed into our brains to, for instance, to help with our episodic memory or to help with our short-term memory?
Oh, good question. Yeah, I am not involved, but there's a couple programs looking at that, especially for soldiers with PTSD and then and also memory loss. It's very early, but the big problem with putting a chip in there, well, there's several problems. One is just basic. If you put something artificial in the brain, the immune system is going to attack it, and it might get infected. So having these things long term are pretty difficult to keep. And then learning the inputs and outputs, especially in something complicated like a memory, is very difficult. And how can you have a memory if you haven't experienced it and then act on it, right? Because our memories are labile. They change. Every time we have a memory, it kind of changes. So that wouldn't happen with a chip, maybe. One area that is being used that's successful, because it's a little more on the periphery, is motor control. So I have seen chips embedded, and I've talked to people where they embed chips in the part of the brain that controls your arm movement. So someone who's never been able, or had an injury and hasn't been able to move their arms for a long period of time, can then actually, with this chip, control a robotic arm to actually feed themselves and do things like that. So that's there, though you still have the issue of having something artificial implanted in your brain and having to open up your brain to put it there. Yeah.
Those are the mics. There's some people's hands down here.
Hi.
Start here.
Thank you. It was very stimulating and quite interesting. I think it just, again, reinforces the brilliance and the amazement of the brain and the body. My question, I've always read through the years that we use a very small part of the brain in reality, and we were able to, if there's an injury or paralysis, we're able to retrain the brain to take over. Is there any advancement in that area to expand the use of our brain, because we're using a limited amount right now?
Yeah. Well, first of all, I always read that too, and I don't know where it came up that we're only using 10% of our brain at any time. It turns out that's really not true. We're using all of our brain. I think the better way of phrasing is that sparse representation. So our brains are very good at doing the amazing things they do with the least amount of energy expenditure. So we use all of our brain, but our brain is very, only is using parts that need to be used when they need to be used. Now, to get to your question, can you expand it? you know, when I first started graduate school in this area, that it was thought the adult brain was not very plastic. And then shortly after that, they realized how plastic the adult brain is, how much it could change over time, how much flexibility there is. And then at UC Irvine, some of my colleagues work on stroke. And there's a critical period too. If you have a stroke and you start doing very rigorous therapy, that you can recover a lot of function. Or, you know, part of the brain is damaged and not coming back, but there's rewiring that can go on in adults that can overcome this. And one of the, I know them fairly well because they do robotics too. So they have a bunch of robots to keep the person, you know, encourage them to actually do these exercises, because sometimes it gets very frustrating when you've had a stroke to do these exercises. And so they're tuned to actually be, you know, invigorating and get the person excited about doing the exercise, and also recognizing when it's too much or too little for them. Yeah, so, yeah. But the take-home message is we're using all the brain, and actually it's extremely plastic, even in adult.
There's been some work in healthcare. I know of one particular study that was done with University of Pennsylvania and UPMC, where they developed a smart patient room. Are you familiar with that?
Not too familiar, but I think I know what you mean, yeah.
And the second part of my question is related to predictive values with diagnosis and prognosis of disease.
Okay. Well, smart rooms I find very interesting, but from my robotics standpoint, and this is sort of a kind of a philosophical decision I made, you know, between using a smart room or a virtual environment, or having the system be in the system being smart and interacting with the regular environment. And from my standpoint, not only is it more interesting, but I think it's more flexible if the system itself is smart and can deal with all the complexities of the world. Because the problem, though I think smart rooms, especially in a hospital, are probably very good because it's a controlled area. But, you know, once you leave the smart room, you lose all that. Let's see, diagnosis. So this is not something I do per se, but a lot of my colleagues in artificial intelligence, what they are really good at is crunching a whole bunch of data and then making very accurate predictions, and very fast. And that's one of the reasons why there's a lot of interest, and it's for good reason. First of all, we have better computers, so we can run these things. They take a while to train, so they get very good. So we have better computers that can do that. And the second thing is, in this society now, we have tons of data at our fingertips. So first they started like recognize the difference between cats and dogs and playing games like Go, but now I see a lot of people going into diagnosing disease. And there's a group at UC Irvine that's doing cutting edge work there too, but it's happening around the world because that's perfect. There's tons of data out there. Doctors are overworked, have to make split decisions. So these things can just crunch through numbers and make predictions and assist doctors in making better diagnoses.
Hockey.
Two questions. One is that you touched on the subject of children with autism. And the second question is, what is artificial neuron?
Oh, let's see. We'll do the autism one first. Like I said, I came in that serendipitously. And autism, typically the key features of autism spectrum disorder is not making eye contact, repetitive behaviors, things like that. But as you know, with our touch robot, as I read more, there's also a thing that's not looked at as much. All the robots to assist them are just trying to, get your attention and make sure you're making eye contact with the robot. But talking with people and reading some, it turns out that children with autism have issues with that kind of what I call hedonic touch. They don't like being touched, a lot of them. And they actually have issues with how they touch things. There's sensory motor problems. So that, I think, has been, except for a few groups, has been ignored in the therapy for autism. And some of the best therapy is to have this multimodal situation where you're playing with the child and working with them, touching them, having them do like seeing, smelling, all these things at once. And that seems to help if it's very rigorous. Okay, that's part, well, I had that artificial neuron, which, it turns out if you know a little bit of math, and I know a little bit of math, the equations governing the dynamics of a neuron are some very simple differential equations, if you call differential equations simple. But and my math is pretty rusty. But you know, you can write it down in a couple lines, the equation, and code it up into a computer program. And it really just governs what triggers the neuron to fire a spike, and then how often that'll happen. And the waveform of a neuron activity has a certain signature. So with a few equations, you can mimic that. And then the other thing that takes a lot of work, or is another set of simple equations, is what happens when there's a connection, which is called the synapse. Like, how does the message from one neuron get to another neuron? So there's equations for that, which aren't too bad. And then how does the connection, that synapse, change over time? Because that's where learning happens. And so those equations aren't too bad. So what the real problem from my standpoint is, we have billions of neurons, and our models have millions. Our models are not as big as a real brain, but they have millions of neurons, billions of connections. So how do you do all of those equations such that the robot can keep up with the real world? That's the hard computer problem. So we found ways to do that, actually.
Back in the back right.
Doctor, we have a partial explanation from you, but when you have these neurological problems, spinal difficulties, or physical injuries, how does that affect, in your studies of the artificial, create a memory loss or slowdown of recall? Is this something that you're working on the neurological end for the patient? Is that robot or just the information you develop going to improve that, because the memory, as I find for myself, is there, but not when I want to recall it. So it's very difficult. And will robotics or the research for the robotics have a beneficial effect to improve that cognitive capability?
Oh, that's a tough question. I guess what I can say is myself and many others are studying memory systems at many levels. And this gets to sort of the mantra of this field of understanding through building. So if you build a memory system and then figure out how it learns and what makes it learn better, or another issue is when there's some sort of damage or loss, how does it recover, and can it recover quickly? So we're building artificial systems to study that. And the hope would be that by studying those systems, we might learn something more about how you retrain things that might lead over to us for helping us learn or recall things. And it's a tough area. I think the good news is brains are very plastic, so they change over time. You can learn things over time, and from the evidence I've seen, this is not my work, but keeping active, both exercising or just being active and keeping yourself mentally active and engaged is a huge part to keeping memories going. Yeah.
Dr. Two more questions in the back.
Thank you. Autonomous cars. Really a great idea, because as we get older, our children take our keys away from us. So my question is, for our grandchildren, where can we get them more involved in these things so that there are more people across the country getting into jobs and trainings at young ages, they're 6, 7, 8, and wanting to do this, so that also they have paying jobs as they get older?
Yes, that's a great question. And it's one of the issues I think about too. We do really have a shortage of technical know-how. So I really, and there's a lot of nice programs that get children involved. I've helped out with a lot of robotic programs at the K through 12 level. And they get children excited, but One thing I will say, and I think I've noticed in this country, if you notice my last slide with the lab, it's very international. I don't think our kids are getting the fundamentals they need. It's what I've seen at the college level. I really think we need to emphasize STEM, and especially the basic foundations of math and programming, because that'll serve them. That's where all the jobs, I think, are going to be in the future. And I think it's harder. This is one thing I find that's harder to do when you get older, at least in my standpoint, is learning a lot of the complex mathematics. So having that foundation coming into when you're at the level where you're trying to think of what job you want, I mean, that'll serve you well no matter what. And now it is a computer age, so I think being able to do some computer programming at an early age, whether you want to be a software programmer or not, just knowing how computers work is going to be very important. Yeah.
One final question right here.
Yes, Doctor, thank you for the wonderful program. Industry is having naturally robotics is getting more and more involved in our industries. And it's also causing a job loss in industry. Even though it's cutting the cost of doing business, it's wonderful, except we're also losing jobs. And how do we overcome that? Is the government stepping in? Are you working with the government at all with that?
Yes, actually there's a government program that's from the National Science Foundation that's addressing that very issue. I don't think of it as job loss. I think of it as job turnover, which is still upsetting, right? Because there's going to be some shifts of jobs. So to answer, follow up on the last question, I think if you're savvy, you should look into what the field is going to be, which is going to be I don't think robots are going to replace people in a lot of areas, and I think there's going to be need to be engineers and computer scientists to build and make new artificial systems. So that's one of the reasons to go, that I think it's bad for some of the people that they're going to lose jobs, but for the next generation, they'll move to this new technology, which is like any technology. And just to give you a autobiographical story, when I was not the best undergraduate student, but I was pretty good at computer programming, and I liked it. And I said, well, if I do okay in computer science, I know I'm going to get a job, because and that was in the 80s where the field, where the jobs were. And so I made a very, I guess at the time, smart decision to stop taking my economics classes, because I didn't enjoy them as much, go into computer science, and that kind of led me on this path. So I think for the next generation, they should look at what they're good at, what interests them, but also, where does society need new brain know-how?
I have a question.
There's actually one more, and that's in the back.
Yes, I enjoyed your talk a whole lot. Over the Thanksgiving, my nephew came to the house, and he had these 3D virtual reality glasses that you could wear. And it was the most incredible thing I've ever seen in my life. By simply running, and what the point of this thing is, you have handicapped people who are paralyzed, automobile accidents or whatever. They just lay in bed. Why not have a system where they could have virtual reality? Over the Thanksgiving, I got to climb virtual reality up to Christ the Redeemer in Rio, Brazil. It is tied to Google Earth. And when you turn your head to the left, it was just like you were there real. And what a thing for the handicapped people that can't do physical things, where they could still have a fun life. Can you talk a little bit about the research on that?
Yeah, I mean, virtual reality, it's been around for years, but seems to be coming of age. I still find the virtual reality systems, when I've used them, still kind of clunky. There's issues because they don't match the world, so there's issues of nausea. But there's still some amazing things that people can do, and the systems are getting better. And over the summer, I actually went to Christ the Redeemer in Rio, and I should say there ain't nothing like the real thing. So from my standpoint, I would say that maybe it would be better not to do virtual reality, but to do technology that makes people handicapped be able to actually experience these things live instead of having some virtual system.
Thank you so much. I think this kind of study points to what it means to be human as well, you know, and it's a real helpful study. We're so grateful for you coming. Thank you. And look forward to next week when we talk about aging brain health, which is following up on this very nicely. Yeah, excellent. So see you next week. Thank you. Thank you very much.
Oh, my pleasure.
It went really well.
Oh, good. That was a lot of fun.
Yeah. Right down the line.